Okay, so in this video, we will consider three problems of intersection in R3. Let's begin with our first problem, number 1. Consider, say, two planes in R3. So we'll call the first plane pi1, given by the equation 3x, negative 2y, plus 4z equals positive 7. And let's consider pi2, our second plane, with equation 2x plus y minus z equals positive 5. As always, whenever you have a plane, it's good to write down explicitly its normal vector. So n1 is the normal vector of the first plane, given by the coordinates 3, negative 2, 4. And 2, the normal to the second plane, where the coordinates are 2, 1, negative 1. And what we want is to find the points of intersection between these two planes. And there's a very concise way of writing this. We simply write pi1, this little symbol called a cap, pi2. So this symbol means intersection, and so we look for the intersection between plane 1 and plane 2, and the intersection, of course, is where the two objects meet in space. Therefore, we're looking for points that are common both to the first and the second plane. So we're looking for points in R3, therefore, with three coordinates, x, y, z are the unknowns, the unknown coordinates of the unknown points, and this point has to belong, or point P must belong to pi1 and simultaneously to pi2. That is what the intersection means. When we look for points in R3, we don't know what they are just yet, so the coordinates are unknowns. But if a point belongs to the intersection of the two planes, that's where the planes are meeting, therefore this point, must be a point on the first plane and simultaneously on the second plane. Before we solve this problem algebraically, let's look at the possible number of solutions that we might expect looking at this geometrically. Well, think of it in two ways. Either the planes are parallel or they're not parallel. Let's draw two parallel planes, and suppose that one is on top of the other. Suppose this were pi1 with the normal vector n1, and suppose that it is parallel to pi2, so pi2 would be lying underneath it. This is the first plane. This would be the second plane, pi2, with its normal vector n2. And of course, if the planes are parallel, there are only two possibilities, right? If the planes are parallel and distinct, they will never intersect, so here we'll get no solution. They could be parallel but the same plane, therefore every point on the plane is a point of the intersection, and we'd have an infinite number of solutions, and that's it. But if you notice, the only way two planes can be parallel is if the respective normals are also parallel. So let's see if that's our case with these two planes. Remember, the vectors are parallel if one is a multiple of the other. Well, look at here. Is n1 a multiple of n2? Well, what times 2 is 3? It's 3 over 2. But clearly this vector n1 is not 3 over 2 and 2, because 3 over 2 times 1 is 3/2, which is not negative 2. And 3 over 2 times negative 1 is negative 3/2, which is clearly not 4. So clearly here, the two normal vectors are not parallel. So our planes are not parallel. Well, let's look at now, if the planes are not parallel, what will their intersection look like? So suppose that I draw one plane like this. Suppose this is pi1. And now pi 1 and pi 2 are not parallel. So imagine that pi 2 is slanted. Like this. This is your second plane. And you can visualize the intersection. If you cut through this plane with this plane, what you will get will be a line, right? Imagine holding two pieces of paper at an angle from one another, where the two pieces of paper meet will actually form a line in space. And so whenever the two planes are not parallel, therefore whenever their normals are not parallel as vectors, the intersection will give you a line in R3. So this will be the line of intersection between pi 1 and pi 2. So we know that in this case, since our two normals are not parallel to each other, the planes are not parallel, and so their intersection will be a line in R3. So we expect to find the equation of a line in R3. Well, let's ask now, how do we algebraically find this line? Well, if you think of it, the points of intersection, the points lying on both pi 1 and pi 2, are points on the two planes. But how can we test whether or not a point is a point on the plane? Well, a point is a point on the plane, pi 1, if it is a solution of the equation of the plane. So the values of x, y, z must solve this equation, but the point is simultaneously on pi 2 as well. So the coordinates x, y, z must also solve this equation simultaneously. So both equations must be satisfied, and so x, y, z are the solutions to this linear system. So you see, before, when we first looked at linear systems of three variables x, y, z, if you only had two equations, what you were doing geometrically was intersecting two planes in the three-dimensional space. But now we're good to go. We've just said that the points on the intersection, lying on both planes, must solve simultaneously both equations. Let's solve the system, and we'll have the equation of the line. Let's rewrite the augmented matrix of the system. So x, y, z. The first equation, if you recall, was the coefficients 3, negative 2, 4, and a constant term of 7. So 3, negative 2, 4, constant term of 7. The second equation, coefficients 2, 1, negative 1, and a constant term of 5. And now we're good to go. Let's row reduce the system, and we'll find the equation of our line. Well, let's do row 1 minus row 2 to get our first leading one. And I will not write here the row operations. I leave that up to you. We're only changing the first row. We copy the second. So 3 minus 2, 1, our first leading one. Negative 2, negative 1, negative 3. 4 minus minus 1 is 5. 7 minus 5 is 2. Then we're going to kill this 2 with the leading 1 by doing row 2 minus 2, row 1. We copy the first row. We're not changing it. And if you perform row 2 minus 2, row 1, you will get 0. 7 minus 11, 1. We want our second leading 1, multiply row 2 by 1 over 7. Recopy the first row as we're not changing it. Multiply row 2 by 1 over 7, and you get 0. Second leading 1, negative 11 over 7, 1 over 7. And finally, we want the reduced echelon form. So we'll kill this negative 3 by doing row 1 plus 3, row 2. We are not changing row 1, so you can recopy row 2. Perform row 1 plus 3, row 2, and you'll get 1. 0. 5 plus 3 times this will be 5 minus 33 over 7. But 5 is 35 over 7. 35 minus 33 is 2 over 7. Plus 3, so you'll get 2 plus 3 over 7, but 2 is 14. Plus 3 is 17 over 7. We now have the reduced echelon form of the system, so we can write the complete solution set. And we now have found all the points lying on the two planes. Therefore, we have found the complete intersection of pi 1 and pi 2. Well, let's see. X and Y are leading. Z is free. So you can let Z be, and here we'll try and clear the over 7 here. So we'll let Z be 7t. Then if we solve for Y, it will be 1 over 7 plus 11 over 7Z, which will give us plus 11t. And let's solve for x. X will be 17 over 7 minus 2 over 7z, but minus 2 over 7 times 7t will give you minus 2t. And t is a free variable, so it ranges over all real numbers. And now we have the so-called parametric equations of the line. Given any t, plug in for x, y, z, and you have a point on this line. If you want, you can write the vector form of the line. The constant terms, if you plug in t equals 0, you'll get the point 17 over 7, 1 over 7, 0. This will be the point on the line, so 17 over 7, 1 over 7, 0, plus t times the coordinates of the vector, -2, +11, +7, where t again ranges over all real numbers. And you see, by writing the points of intersection this way, it's clear that we have a line, because we take an arbitrary, well, not an arbitrary, but a given point in space, say p naught, and we add to this point any multiple of this vector. So this is our directional vector of the line. This is one point on it, and you see the intersection, as we claimed geometrically by looking at the picture, is indeed the equation of a line in space. You can either leave it as the parametric equations, or you can rewrite the line in its vector form. So this is how you intersect two planes. Of course, if the planes were parallel and distinct, in the end you would have an inconsistent system, therefore no point of intersection. Let's consider now a second problem of intersection. What if we were to intersect, say, a line with a line? So now, instead of two planes in space, two lines in space. So problem 2. Let's take two lines. Let's write them in vector form. So line 1, given say by 1, -1, 3, plus arbitrary multiples of the vector -2, 1, 2, where implicitly again t ranges over all real numbers. And let's take line 2, also in vector form. The anchor point will be 0, 10, +4, plus arbitrary multiples of 1, 3, -1, which is the directional vector of line 2. Okay, so again, you can think of it geometrically. This is actually simpler than two planes. If you have two lines in space, either they don't intersect and you get no solution. If they do intersect, they could be the same line, and therefore every point is a point of intersection, or they could be different lines, and if they do intersect, we get a single point. Well, clearly, if you look at the two lines, call this P1, the anchor point of line 1. Call this V1, the directional vector of line 1. Same thing here, this is P2, the anchor point of line 2. This is V2, the directional vector of line 2. And clearly these two lines are not the same, because look at their directional vectors. This is the vector 1, 3, negative 1. This is the vector negative 2, 1, 2. If the lines would be equal, they would have to have parallel directional vectors. Well, clearly V1 is not a multiple of V2, because if it were, well, negative 2 is negative 2 times 1, but negative 2 times 3 is negative 6, which is not 1. So clearly V1 cannot be a multiple of V2. So these two lines are not parallel. So either they will not intersect and we'll get no solution, or if they do, we'll get a unique point. Now the question is, how do we figure out algebraically how to intersect these two lines? It may not be obvious in the vector form, but it will be if we write the parametric equations of both lines. Now you have to be careful here. We're using t in both cases, but t here is a dummy variable. It ranges over all real numbers. Now even if the two lines do intersect, you may get the point of intersection using different values of the parameter for both lines. So we'll have to change the value of the parameter in at least one of these two lines, because if we don't, implicitly we'll assume that the two parameters will have to be equal to give the point of intersection, and as we'll see, this is not always the case. So we'll keep t for line 1, but we'll replace t by s for line 2. If you were to add p1 with tv1, you would find an x-coordinate of 1 minus 2t. You will find a y-coordinate of negative 1 plus t, and a z-coordinate of 3 plus 2t. So any point on the line must have an x, y coordinate equaling to this for some value of t. Let's look at line 2 now, and its parametric equations. As we've said though, we'll change the dummy variable t here for s. So x would be 0 plus 1s, so just s. Y will be 10 plus 3s. And z will be 4 minus s. And now this will be much more obvious, because what do we want here? As we said, we want the intersection between line 1 and line 2. This is where the two lines meet each other. Well, we want the points, x, y, z. Again, these are unknowns. We don't know what the coordinates are of our point yet, but this point must belong to line 1 and simultaneously line 2. Well, now think of it. If this point is on line 1, there has to be a value of t that will give you x equals this, y equals this, and z equals this. So these equations must be true for some choice of t, but simultaneously, the point P also is a point on line 2, so there has to be an x value where the coordinates x, y, z are equal to these three functions of s. So these equations must be true, and the same goes for these three as well. Well, we can equate them. X must be equal to 1 minus 2t for some choice of t, and x must be equal to s for some choice of s. So 1 minus 2t must be equal to s. Similarly, y must be equal to negative 1 plus t for some choice of t, but y must also be equal to 10 plus 3s for some choice of s. And finally, z must be equal to 3 plus 2t for some choice of t, but z must also equal 4 minus s for some choice of s. Once again, we have a linear system and two variables, three equations. And if we solve this linear system, we'll have the values of s and t that will give us, as we've said before, our unique point of intersection? Well, every time we want to solve a linear system, we have to rewrite it as all the variables on one side, all the constants on the other side. So let's do this here. I'll send the t's onto this side, the constants on the other side, so this will become s plus 2t equals 1. This will become 3s minus t equals, well, negative 1, negative 10, negative 11. And finally, negative s, negative 2t equals, send 4 over here, 3 minus 4, negative 1. And now we're good to go. Let's write the augmented matrix and then solve the system. Keeping in mind S for the first column, T for the second. We'll have 1, 2, 1, our first leading 1. 3, negative 1, negative 11. And here I'll negate this row, and it will become 1, 2, 1. Well, let's do row 2 minus 3, row 1, row 3 minus row 1. We copy the first row, we're not changing it. Let's do the easier one first. Row 3 is equal to row 1, hence row 3 minus row 1 is 0. So this row becomes vacuous. It says that 0 equals 0, so we can drop it. 3 minus 3, 0. Negative 1, negative 3 times 2 is negative 6, negative 7. Negative 11, negative 3 is negative 14. Multiply row 2 by negative 1 over 7 to get a 1 and a 2 here. We will drop the third row. It's not giving us anything. It's saying that 0 equals 0, so we don't need it. And we'll have 0, 1, 2. We have our second leading 1. We can now kill the 2, doing row 1 minus 2, row 2. So 1, 0. 1 minus 2 times 2 is 1 minus 4, which will give you negative 3. And now we have our solution set. There is a unique solution, S equals negative 3, and T equals positive 2. And let's see now, we have found the two unique parameter values to give us what we hope is the point of intersection. Let's see if in both cases we get the same point. So S equals negative 3 will give us the point. Let's go back. The parameter S was for the second line. If we replace now S by negative 3, we'll have the coordinates of our point. Negative 3, 10 minus 9, positive 1, 4 minus negative 3, 4 plus 3 is 7. So we have the point negative 3, 1, 7. Let's see if with our second parameter value we get the same point, and we should, because we're supposed to have found a point that lies on the two lines. So with t equals 2, will we get the same point? Hopefully we will. Well, plug in t equals 2, you'll have the point 1 minus 4, negative 3. Negative 1 plus 2, 1. 3 plus 2 times 2, 4. 3 plus 4 is 7. And indeed, we get the same point as we had hoped. So finally, our conclusion is the intersection between line 1 and line 2 consists of the set containing the unique point, negative 3, 1, and 7. And that's it. So if you visualized this graphically, you can imagine this is line 1, This is line 2. And again, these are two lines in three-dimensional space, and the point where they meet is the point -3, 1, 7. If the lines did not meet, you would end up here with, again, an inconsistent linear system, therefore no solution. Let's do one last example of intersection, and that is, what if we intersect now a plane with a line? Let's take our plane, given by the equation 2x plus y minus z equals 5. And let's take the line, and here I'll write the line already in parametric equations form. If it were in vector form, simply change it to this form, and this will make the solution really easy to see. So we'll say the line is given by x being 1 minus 2t for some t, y given by -1 plus t for some t, and z given by 3 plus 2t for some t. And again, t ranges over all possible real numbers. And we are going to ask for the intersection between pi and L. Well, algebraically, we're looking for points that lie on these two objects, on the plane and on the line. We don't know what the point or points are, so the coordinates are unknown, they're variables. But it has to belong to the plane pi and, let me write and, the line L as well. So now think of it algebraically. A point lies on the plane if its coordinates, x, y, z, are a solution of the equation of the plane. So x, y, and z must be solution to this equation, but the point must also be a point on the line, so there has to be a value of t where x equals 1 minus 2t, y equals -1 plus t, z equals 3 plus 2t. So all of these three equations must be satisfied for some value of t, but x, y, and z must also simultaneously be a solution to this equation. This equation is true, so are these three. So it's not too hard to see that what we can do is replace x by 1 minus 2t, y by -1 plus t, and z by 3 plus 2t, and we'll have one equation into one unknown, and then we can solve for t. Because all of these equations must be simultaneously true. So 2 times x, 1 minus 2t, plus y, -1 plus t, minus z, minus 3 plus 2t. But be careful, you have to negate z entirely, and you'll get -3, -2t. This must be 5. Let's now solve for t. Well, what are we going to have for t? 2 times -2 is -4t, plus t is -3, minus 2t is -5t. Constant terms, 2 minus 1, 1, minus 3, -2, and this must equal 5. So -5t must equal 7. Therefore, t, we have a unique solution, must equal -7 over 5. So there is a unique value of the parameter that will allow us to simultaneously satisfy the equation of the plane and the equations of the line. Therefore, we have a unique point of intersection. And we can easily find this point of intersection because we have the value of the parameter. Plug it back into the line, and you'll have the coordinates of the unique point of intersection between plane pi and line L. So x equals 1 minus 2t. This will give you 1 plus 14 over 5, but 1 is 5 over 5. 5 plus 14 is 19, therefore 19 over 5. is the x value of our point. What about y? Negative 1 plus t. So negative 1, negative 7 over 5, but negative 1 is negative 5 over 5. Negative 5, negative 7, negative 12 over 5. And as that component of our point, 3 plus 2t, well, 2 times this will give you negative 14 over 5, but 3 is 15 over 5. 15 minus 14 is just 1 over 5. And so we have our unique point of intersection. The point P is equal to 19 over 5, negative 12 over 5, and 1 over 5. So if you were to visualize our conclusion, we had the plane pi, and again you can draw an arbitrary plane. The line L and the plane pi meet in the unique point. Obviously they're not parallel. The line L will cut through the plane. You can imagine the line going through the plane, and the point where they meet is the point 19 over 5, negative 12 over 5, and 1 over 5. And that's it. So you see, every time that you want to intersect objects, whether it's two planes, two lines, or a line and a plane, all you end up with is a linear system. Once you solve for it, you find all points of intersection, whether there is none, a unique solution, or an infinite number of solutions.